Hi, this is a continuation on our last lecture on polynomials. Last time we had introduced basic terminologies related to polynomials. We had looked at uh, the long form division associated with polynomials and also a theorem called the remainder theorem. This time we'll start with a theorem called the factor theorem, which is given as such. That is, x minus a is a factor of px if pa is equal to 0, and if x minus a is a factor of px, then pa is equal to 0. Note that these two are not alternate statements of the factor theorem. In fact, these two are converse statements of each other and together constitute the factor theorem. Uh, we can obviously see how this holds true. That is, PA is the remainder of the division which we get on dividing px by x minus a according to the remainder theorem that we had done last time. And so therefore pa should definitely be equal to 0 if x minus a is a factor of px. So therefore you naturally get some intuition as to why factor theorem needs to be true. And we will look at say let's consider the polynomials we had taken up last time. That is 5x cube minus 2x square plus 3x minus 2, and we had divided it by x minus 1, and the remainder, if you remember correctly, is coming out to be 4, and the remainder comes out to be 4. That is, pa comes out to be 4 and therefore not equal to 0. And so therefore we can say that x minus 1 is not a factor of px, that is this polynomial right here, and which is confirmed by long form division that we had done last time. Now let's pick up another case. Let's say x square plus 5x 5x plus 6, and consider x minus, let's say, x plus 2. Now if we find out p of minus 2, we get, let's say this is p x, and we get p of minus 2 is equal to minus 2 whole square plus 5 into minus 2 plus 6, that is 4 plus minus 10 plus 6 is equal to 10 minus 10 is equal to 0. And so therefore we know that x plus 2 is actually a factor of px, that is x square plus 5x plus 6, and we can confirm that by long form division. Now it is time to recall some identities that we have learned from earlier classes. That is, x plus y whole square is equal to x square plus y square plus 2xy. X minus y whole square is equal to x square plus y square minus 2xy. X plus y into x minus y is equal to x square minus y square, and x plus a into x plus b is equal to x square plus a plus b x plus ab, and x plus y plus z, this should be whole square, is equal to x square plus y square plus z square plus 2xy plus 2yz plus 2zx. Now these identities will come in very handy when you talk about, say, factorization of polynomials and other operations or manipulations that we need to do with polynomials that we have in our hands. We will look at factorization using this identity in particular. Say, let's consider the polynomial px is equal to x square plus 5x plus 6. Remember, this is the one we checked a factor for while we were discussing factor theorem. So let's look at factorization using this identity. This using this identity is in a way called splitting the middle term, and splitting the middle term is splitting this such that splitting the number 5, or say the coefficient of x to the power 1, in such a way that those two numbers multiply and give this number. That is splitting the middle term into factors of the constant coefficient. That is the coefficient of x to the power 0. So the factors of 6 can be written as, say, 1 into 6 or 2 into 3. Those are really the two factors, two ways to factorize you can think of. And so 2 and 3 look promising because you can add 2 and 3 to give 5. And so therefore let's write 5 as 2 plus 3. So therefore px is equal to x square plus 2 plus 3x plus 6 is equal to x square plus 2x plus 3x plus 6 is equal to x plus 2, that is taking out x common from these two, and on taking out 3 common from these two we get x plus 2, and now taking out x plus 2 common from these two terms we get x plus 2 into x plus 3, and so therefore px, which is given by x square plus 5x plus 6, can be factorized as x plus 2 into x plus 3. We had, remember, proved that x plus 2 is a factor of px while we were discussing factor theory. Also, note that these identities are not just useful while we are discussing arithmetics, while we are discussing polynomials. They can in general be used to say make your calculations easy or something of that sort. For example, let's consider taking out the square of 105. Now this might involve a lot of computation, but another way to do this would be to say we're taking out 100 plus 5 whole square is equal to, now this is this can be simplified by using this here, this identity, and so we can write this as 100 whole square plus 5 whole square plus 2 into 5 into 100. You see how the computations get much easier, and you don't have to find out the square of a 3-digit number. We will leave the calculations as an exercise, and you can verify that. Some other identities which will come in handy while doing polynomials or mathematics in general are these three. X plus y whole cube is equal to x cube plus y cube plus 3xy into x plus y. This can be found out by multiplying x plus y into x plus y whole square and expanding this using this theorem. On doing that you will get this, and similarly x minus y whole cube is equal to x cube minus y cube minus 3xy into x minus y, and x cube plus y cube plus z cube minus 3xyz is equal to x plus y plus z into x square plus y square plus z square minus xy minus yz minus zx. Now these three identities are also very useful and will come in handy when we are doing polynomials or other mathematical computations. This is all we had to say on polynomials. Thank you so much.